Hello and welcome to this talk on digital manufacturing engineering. My name is Andrew Longstaff. I'm a professor in the School of Computing and Engineering at the University of Huddersfield. When I was choosing my degree, I was doing A-levels in maths, physics and economics. I very much liked maths. I liked science. I went on to do a maths degree. But after that, I was trying to work out what I was going to do with maths, and I was really interested in applying it. So I came to Huddersfield University and did a master's course in engineering control systems and metrology. Metrology is the science of measurement. And I found it really exciting to be able to apply the mathematics that I'd learned to something that is really useful. So I went on and did a PhD. And my PhD is in manufacturing, around making machine tools better, so we can make things better. Having done that, I then ended up on the staff, and I'm now a professor. I'm a research director, which means I decide what fun things we get to look into next, what are the new challenges. But I'm also course leader for digital manufacturing engineering, as well as that control systems MSc that I learnt all those years ago. Still not sure where I'm going to end up, but it just gives you an idea of that career path that I've been on, and how at school I knew nothing about manufacturing, and now it is my life. So what are we going to cover today? What is digital manufacturing engineering? It's an interesting set of words. Then I'm going to just talk through some careers, and I wouldn't necessarily advise you to go down the route I did, but I've seen lots of different potential careers in industry, and we can talk about those later on. Then I'm going to give you an overview of the course, a brief run through of the entry requirements, and then this is one of your big decisions in your life. There'll be some further links that you can go to and find out what it's all about. Don't just take my word for it. So one thing that we often get asked is manufacturing. Do we still do that in the UK? Well, set aside the fact that the UK is part of an international market. Yes, we do. These images just represent a number of the things that we're really good at. So in the UK, we're making bits of Formula One cars. We're making engines. Little known fact is we've got some of the most advanced engine manufacturing facilities in the UK. But we make all sorts of other things. Aerospace, we make bits of aeroplanes, aeroplane engines, we make satellites, electronics, all sorts of things. So do we make things in the UK? For sure we do, and the government has recognised that this is an area that we need to grow to balance the economy. So at the moment, and for the foreseeable future, there is a lot of emphasis on trying to look after the next generation of engineers and the next generation of people who can make things. So why are we talking about digital manufacturing engineering? Well, one of the things that's come about in the last 10 years is that we want things that don't cost as much. So the power of the processor in the mobile phone in your pocket comes at a price. But we can make it through mass manufacturing very cheaply. But we don't all want the same thing. So this drives us towards something called mass customization, which means that we get the low prices by making things very efficiently, but we can choose to modify them so that we've all got our own little twist on it. These are just 4 examples, some slightly more advanced than others, shall we say. So the top one there just represents the BMW Mini, where there are a core design of a car, but then so many options so it can be personalised. I visited the factory a few years ago, and it was the first time they'd actually made a second identical car in the several years of production that had been going on. We'll all have seen the rise of being able to put your name or the name of a loved one on a product. We couldn't have done that years ago. It took an artisan to be able to individualize products at a great cost. Now you can upload images or you can upload simple text and have something through the post in a day's time. I'm sure you've all used famous websites to get a greetings card individualised, or a wine glass perhaps, or in my case a beer or whiskey glass. Things like trainers, things like earbuds that can be modified just by either you providing information or by, in the case of the earbuds, taking some photographs with a camera of your ear, uploading those, they get processed, and then you get the earbuds that match the shape of your ear. This technology is really exciting, and this drive is what is taking us towards digital manufacturing. So instead of the old way, the traditional method of somebody with a sheet of paper doing a drawing, it gets sent down to a factory floor and someone programs a machine to make it. We now want to be able to seamlessly come up with the ideas in our heads, put them into a software simulation that we can test and check and validate it's going to work, then make the part, and then see does it work correctly. So you can see this flow all the way from design through to doing simulations on a virtual machine. In this case I've shown a milling machine, that's what I love, but it can be a robotic system, it can be a 3D additive metal or plastic printer. We can see what the product's going to come out like. We can then get two of these products that we've virtually created and put them together and see, do they fit? How well do they fit? How do they perform in service? And we can do all sorts of analysis, and this is the heart of digital manufacturing engineering. But what's even stronger now is this bit in the middle, in-process monitoring and control. This is something where in the past, in the very recent future, and even now, we relied on people, experts in driving the machines, to touch it, to feel it, even to smell it. And if it's not coming out right, they could make adjustments. With mass manufacture, we couldn't do this. We just had to rely on the repeatability, the reproducibility of parts. One of the really exciting things in digital manufacturing is that we are gathering data from all of the machines, all the way through the process flow, so we can make sure the part that comes out at the end actually will come out right. We talk about verification. We should know from all the data that's coming earlier on in the track that it's going to come out right, and that is really just a tick box at the end. But better than that, if it isn't quite right, we should be able to match that back to the digital model at the start and make improvements, either to the design or to the process. And this is what a digital manufacturing engineer will do. They will look at the entire set of systems in a process, break them down logically, apply design intelligence, design creativity to make the product better and make the process better. There's a term that's often used at the moment, which is Industry 4.0. It's a nice tag to hang things on, but really all it's saying is that we should be able to have a process by which we can very easily make specifications, make them right, and make them so that there's no issue with getting the right product at the end. We then monitor all the things that are going on in the middle. Now this is not just the product on the machine tool that's making the part on the milling machine. It's also the logistics. It's, can I get the raw materials when I need them? Can I get the spare parts to maintain the machines to make my new product? Wherever possible, we look at automating where it's the right thing to do. So this isn't about taking away jobs of people, this is about using people in the right way. With robotics, we often say, if it's dangerous or it's dirty, get a robot to do it. We don't want to put humans in those situations. We want to give humans jobs that are interesting, that are creative. We don't want to give them repetitive tasks. And then using the big data that comes out of it, again, we make informed decisions. So somebody coming into an education into digital manufacturing engineering is at the creative heart of how we achieve this. It's not about standing in front of a machine tool every day, pressing cycle start. This is much more about the design, the engineering behind how the process works. I'm just going to show you one quick example of something that's been done within my research group. So you may have heard of the Large Hadron Collider, the search for the Higgs boson. This is a project that we did with CERN and in the UK STFC. One of the things that the CERN accelerator does is fire a beam around the entire site, a beam of energy which we want to go in a certain direction to be able to make that circuit. We use a collimator in order to guide the beam. Now, what can happen as the beam of energy goes around the CERN accelerator is that little bits of the energy stray off. In the worst case, the beam completely drops out of alignment, out of the suspension, leaves the beam pipe and dumps the equivalent of 3 to 4 sticks of TNT at one go. So what we were looking at was a new design of a collimator, taking a new mechanical design that allowed us to make adjustments. So if any of that energy hits the collimator, we can make a rapid adjustment to it. So that of itself is a mechatronic engineering problem, how to design that. But what we wanted to do was look at the manufacturing side of it as well. So here is a design of the new collimator using some quite exotic materials that were required to fit into that high radiation environment. Actuators, which are the bit that allows us to make adjustments, and sensors that mean that we can detect there's been something bending and we can push things back into alignment automatically. We've then got to think about the control loop. In terms of manufacturing though, we wanted to make sure at this very, very early stage that we could capture and validate that it was going to work. So we drew it up in CAD. This is something you would learn in the first year of this degree. We did analysis. Again, this is finite element analysis, where we can apply a force and see what the response is all the way along, so we can see areas where there's high deflection or low deflection. So we virtually tested it. We then machined it on machines in the workshop at Huddersfield University. Again, some of the interesting things, the lessons learned from that, are just how the materials behave. You can see here the machine doing the machining. We've had to apply clamps to stop it springing as it machines. Traditionally, this is something that the craftsman would work out how to do and then retain in their brain. So next time it comes along, assuming that craftsman's available, we'll get it right. If not, we have to start again from scratch. With digital manufacturing engineering, we're looking at how we capture that knowledge and feed it back to the design process. We then had to go through the assembly and make sure that the assembly we'd virtually tested worked in real life. And then the final quality inspection here using a measurement arm, again in our lab at Huddersfield University. We made sure that if we applied a force that we could correct it using our measurement instruments. And that part has now been made and is going to be shipped to Switzerland. The ideal next step would be it's tested in real life, and that digital twin of the manufacturing process, we can see how it responds through life. So the degree itself, the idea of digital manufacturing engineering, is very much grounded in engineering, mechanical engineering. But data analytics and the analysis is just as important. We've got the data. We've got human knowledge and experience. Yeah, we've got some hard maths. That's really important. But we've got the new technologies coming through. So machine learning, deep learning, artificial intelligence, as some people call it. These tools are enabling us to take all of this masses of data from the design and the manufacturing process and do something with them. So as well as mechanical engineering, the course needs you to understand things like data analysis, things like how to protect that data, so cybersecurity. The core is still mechanical engineering, but you need to understand the other systems that come into play. Just going back to who manufactures. A lot of the things that I will talk about on this talk have been the fields that I work in, but it isn't just about aerospace. The same techniques are being used in pharmaceutical and biotechnology, in making things for energy and sustainability, fabrics, paper supply, transport and mobility, media, culture, technology and entertainment. So how do you make the parts that make the screens for the TVs? Aviation, aerospace and aeronautics, materials, nuclear, mining and chemicals, agriculture and food, construction, engineering and infrastructure. So it's not just about the high precision, it's all the way through to how you make bags of crisps. Now in this degree you will learn the principles, but the techniques, the ideas behind digital manufacturing engineering can be applied across the board to all of these sectors. So now just a little bit about the degree in more detail. As I said, the fundamentals are, it is an engineering degree. Engineers need to understand maths. Beyond that, we are looking at the core things that we need for engineers, mechanical engineers, but also the manufacturing side of it as well. So we've got mechanical engineering and science, manufacturing technology and workshop appreciation, robotics and mechatronics, engineering, communication and materials, and professional development and transferable skills. The important thing that you can see from this is we get the maths, we get the mechanical science, but we start to see some of those things that are important in manufacturing. So we use robotics a lot, or automation. We understand how the mechanical things integrate with the control systems. This is a really important skill that often gets missed out. We make sure this is embedded in the first year. We understand how to communicate engineering concepts and understand materials properties as well. So how do we get the drawings and make sure that there is a true thread all the way through from your concept design to the manufactured product? And then it's not just about the technology, it's about how you can build yourself as an engineer and as a future worker. So professional development and transferable skills are really important in making sure that you're ready for the world of work, and we start that from the first year. In the second year, we start to diverge from some of the other mechanical engineering courses. So in particular, production control systems has been designed particularly to think about all of the aspects of digital manufacturing engineering that are needed. We also embed cybersecurity because of all that data flow. If we are going to change the world, enabling us to gather all of this data and analyse it, we have to make sure that it is trusted. So cybersecurity issues are really important. We're also looking at the application of the techniques from year one into manufacturing and into the innovation required to take products to market. Again, fundamentally, with manufacturing, we need to understand design, CAD, which is computer-aided design, and CAM, which is computer-aided manufacture. That is taking those design parts and putting them onto a machine. So if you've ever done any 3D printing, you'll know that you can create a design in CAD, send that to the machine, and it will be able to manufacture it. That transfer there is okay for, let's say, toys, for pieces of art. When we get to things which need to be at the level of 1/1000th of a millimetre or 1/1000th of a metre, then it's really important that we understand that surface level defect, how bumpy it is, and that geometric feature of how well things fit together. And then signal analysis and control, again, really important, is this blend between the mechanical engineering and the control systems and how we deal with the data. And as you'll probably have heard, rubbish in, rubbish out. If we don't make sure our signals are correctly filtered and analysed before applying control, we can take something and make it a whole load worse. Third year is the placement year. This is an opportunity for you to go out and do a year of work as part of your degree. This is a really successful initiative. I speak to a lot of employers and they really like this aspect of our degrees. It provides you with that 1 year where you are taking your knowledge and applying it, but also working alongside colleagues in industry. It gives you something to talk about. It's also the possibility to get paid while you study, enhance your CV, and as I said, your employability prospects are much higher having done it. We also find that the students come back with a level of maturity, having worked alongside people on the factory floor in the design office. So this is a really positive aspect of the degree. And then in the final year of the Bachelor of Engineering, we again specialise a little bit more. So factory simulation systems are looking at how we take that physical world, convert it to a digital twin, and then we can do not just the analysis of the product, but the analysis of the product during the manufacturing chain. So here you can see one of our machine tools at the university, and this is a computer-aided engineering model that we have made of the machine. The level of detail we're going to with this is actually just how good the machine is. So it's not just a machine with 3 moving parts. It's a machine with 3 moving parts that have got a little bit of bend in them, and we are modelling that and understanding what the effect of that inaccuracy is on the parts we make. Now this is really important if you're working with a machine tool, but it's even more important if you're a manager and you want to choose which of those machine tools to use to make the part. So if you're making something high precision, you choose the one that's best. This level of knowledge isn't available to a lot of people at this time. Most people don't understand it, and this degree helps you to understand where these factors come from. We also look at dynamic analysis, so it's not just about simulating, it's about understanding how a product performs, a machine performs in use. And then again, we've got some interesting things that we need to run alongside this. So project quality and production management tell you those skills that don't just mean you technically know what's going on, it means you understand how to implement it in the real world of work. And then we have final year project options, where you could take on something that you've done as part of your placement and develop that further, or we will work with you to come up with a suitable project around digital manufacturing engineering in order to get something that's really specialist to you and will be great for your CV, because it's the sort of thing that you can talk about in depth and show a potential employer exactly what it is that you've learned. There's also some option modules which we've decided to make in order to help people specialise. So the option modules are between control systems and advanced elements of mechanical design. So this means that at this stage of the degree you can decide whether you want to focus more on the design side or move more into the control side. Both are important, but it really will depend just on where you are at that stage of the degree as to which you want to go into. Entry requirements for the degree are on the screen now. And that is all I have to say, and thank you very much for listening. There's some links here to other things that we provide. Thanks so much for your time, and I hope you found this useful.